Hello everyone. So welcome to this turbo machines, and we are studying this steam turbines, which is module number 3. So which is impulse and reaction steam turbines. And in my previous videos that we have seen all the theory part of steam turbines. So we have seen the definition of steam turbines and the classifications and the differences between impulse and reaction turbine, and then how to solve this work done expression, and how to do this blade efficiency derivation, and how to do this maximum blade efficiency. And then so we have moved on to this compounding. So we understood what is all about this compounding, and what are the different types of compounding, like pressure compounding, velocity compounding, and a combination of both pressure and velocity compounding. So after finishing that, we have seen that pressure velocity graph for each and every compounding. So how is the behavior? What is the pressure velocity changes based on the different stages when it passes through the one stage to the other stage? So what are the changes takes place? So all those things that we have seen. And now we have come to an end, and by solving this problem, so we will understand even more better. So we'll move on to the first problem in impulse and reaction steam turbines. And this is the problem. So the problem goes like this: a convergent divergent adiabatic steam nozzle is supplied with steam at 10 bar and 250 degrees Celsius. The discharge pressure is 1.2 bar, assuming that the nozzle efficiency is 100% and initial velocity of steam is 50 meters per second. Find the discharge velocity. So this is the problem which is given. So we will see in little detail. A convergent divergent. So nozzle is taken. So what is the shape of the nozzle? It is a convergent and divergent. What is the meaning of convergent? It is nothing but there is an increasing in area. So first there will be small area, and slowly gradually it increases to the larger area. So that is nothing but the convergent portion. And then there is a divergent portion. That is initially there will be more area, and then so there will be decrease in area. So that is nothing but divergent. So convergent and divergent area. So first one is convergent, that is decrease in area, and divergent is increasing area. So that's why in that way we have to understand. So convergent is decreasing and divergent is increasing. Okay, so that kind of nozzle that we are taking, at the same time it is adiabatic. So what is the meaning of adiabatic? It is isentropic. That means entropy remains constant. So steam nozzle is supplied with the steam at 10 bar pressure. So here initial pressure is given, that is high pressure they are taking, so at 10 bar, and initial temperature is also given, that is 250 degrees Celsius. That means initial pressure is 10 bar and initial temperature is 250 degrees Celsius. So this is the condition of the steam which is entering into the nozzle. Now discharge pressure is 1.2 bar. So that is at the end of the turbine. So the pressure drop takes place and the pressure comes back to 1.2 bar, from 10 bar to 1.2 bar, assuming that nozzle efficiency is 100%. So here nozzle efficiency, so there is, that means it is given as 100%, which says that there is no friction available. There is, in the absence of friction, this nozzle works. So that's why it is given as 100%. And initial velocity of steam is 50 meters per second. So velocity with which the steam enters into the nozzle is 50 meters per second. So find the discharge velocity. So we need to find out the final velocity when the steam comes out from the nozzle. So this is what we need to find out. So we'll move on to this given data. So first one is given as initial pressure, that is P1 is equal to 10 bar. This is the initial pressure, and temperature T1 is equal to 250 degrees Celsius, and exit pressure, that is P2, that is equal to 1.2 bar, and nozzle efficiency is given as 100%, which says that there is no friction, and initial velocity of steam, that is V1 is equal to 50 meters per second. So that means before entering into the nozzle, the velocity was 50 meters per second. So we need to find out the discharge velocity, that is V2 we need to find out. So V1 is given, so we need to find out V2. So from steam table, so we need to take the steam table and take the what you call the corresponding values of the pressures given. So there are two pressures given here. So one is 10 bar pressure, another one is 1.2 bar pressure. So we need to take the steam table and go to this dry saturated steam. So in the dry saturated steam, so we will come across this 10 bar pressure, and T1 is equal to 250 degrees Celsius. So what does it mean? That means the steam is in superheated steam. So before solving this problem, so I would like to tell you the different types of steam available. So there are three types. One is wet steam, next one is dry saturated steam, and the other one is superheated steam. So wet steam is nothing but some amount of water particles will be present in the steam. So that is nothing but wet steam. So dry saturated steam, that is the steam is completely dry and there is no water molecules present. So for the dry saturated steam, dryness fraction will be 1. That means 100% dryness will be there in that steam. And next one is superheated steam. This type of steam will have more amount of energy than the wet steam and dry saturated steam. So here in this problem, so there is a 10 bar given and 250 degrees Celsius given. So that indicates, so it is a superheated steam. So for superheated steam, if you go to the dry saturated steam table, so 10 bar, so and so find out the, we need to check the 250 degrees Celsius. For the 10 bar and 250 degrees Celsius, we need to note down the values of enthalpies and entropies. So H1 is equal to 2943 kilojoules per kg seconds, or kg Kelvin it will be. So 2943 kilojoules per kg Kelvin. And the entropy, so that is entropy is denoted as the letter S1, S, and for initial S1. So that is equal to 6.926 kilojoules per kg Kelvin. So from steam table, so these are the values which is corresponding, so for 10 bar pressure. So you need to go for this 1.2 bar, the same one. You need to take dry saturated steam. So there will be different steams. So first one is for superheated steam, and the next one is for dry saturated steam. So for dry saturated, P is equal to 1.2 bar. So we need to take the values of HF2. That is HF is equal to 439.3 kilojoules per second, and HFG2, that is 2244.1 kilojoules per kg. So for the corresponding entropies, that is SF2 is equal to 1.361 kilojoules per kg Kelvin, and SFG2 is 5.937 kilojoules per kg Kelvin. So here it is given, that is S1 entropy adiabatic process, that means entropy is constant. So for adiabatic, since it is mentioned in the problem, it is adiabatic process, we can take S1 is equal to S2. So S1 is equal to SF2 plus X2 SFG2. So this is SF2 is nothing but the dryness fraction. We need to find out what is the final dryness fraction. Why? Because so for 10 bar H1 is 2943, and for 1.2 bar, so it is coming around 2244.1 kilojoules per kg. So since it is understood that it is wet steam, so S1 is equal to S2, S1 is equal to SF2 plus X2 into SFG2, where X2 conveys the dryness fraction. So if you substitute the remaining values we know, so we need to find out the dryness fraction. So X2 is equal to 0.9373, which is 93.73% of dry is available in the dry steam, and remaining 100 minus 93.73 will be the wet steam. So that is what it says. Now we know that. So we understood what is X2, dryness fraction. The same thing we should apply for these enthalpies. H2 is equal to HF2 plus X2 into HFG2. So we need to substitute these values and find out the final enthalpy. That is H2 is equal to 2542 kilojoules per kg Kelvin. So this is for not Kelvin, this is kilojoules per kg, because for all the heat energies will be, the units will be kilojoules per kg, and for entropies it will be kilojoules per kg Kelvin. Now in the problem it is asked that to find out the exit velocity. So that is V2 is equal to RT into 2000 into 2943, so into 2542 plus 502. So if you substitute all the values are known to us, so if you substitute in this equation, so you will get 896.91 meters per second. So this is the exit velocity of this particular steam. So this is how we need to solve the problems in this steam turbines with respect to this steam nozzles. Okay, so we will solve another problem in my another video. So thank you for watching.